Today, we're going to learn about a new topic, which is called the area moment of inertia. And in today's class, we're just going to spend time learning how to calculate this using integration. And then next time, we're going to do the much more practical application, which is learning how to find the area moment of inertia of composite or built-up shapes, just like we did with centroids last week. Remind you guys, you've probably seen moment of inertia before in physics. So maybe as a little bit of an aside, in physics, you would have seen what's called mass moment of inertia, and this is different than area moment of inertia. What mass moment of inertia was, and the reason that you used it is if you were dealing with, say, a solid circular disk that you were trying to get accelerating in some way by applying a torque to it, versus a hollow ring. Do you remember these kind of problems? I know I did them when I was in physics. And these things have a different amount of kind of mass moment of inertia, meaning that depending on how much torque you apply, they're going to accelerate differently. And we used that when we summed torques and said the sum of the torques is equal to a symbol for mass moment of inertia. I'm not sure what you might have used. It might have been a capital I or something else, I sub m for mass moment of inertia, maybe times angular acceleration, which we used alpha for angular acceleration. So this is the rotational equivalent of Newton's F equals ma. And when you start rotating things, if you add up all the torques that are being applied, you will start to have an angular acceleration, and how much torque it takes to produce a particular angular acceleration is the mass moment of inertia. Okay, that is totally different from what we're doing today. What we're doing today is called area moment of inertia. And where area moment of inertia comes into play is you're going to use it next semester when you are calculating how much a beam is going to bend or deflect and how much stress will be in a beam to figure out if it's going to break or not. So area moment of inertia has a lot to do with bending and flexural stiffness. Here is the picture. If I have an X and a Y axis and I have an area, because we're finding area moment of inertia, we've got a shape that we're interested in. And I want to remind you of a couple of integrals that we've already done in class. The first is, let's say I wanted to find the centroid location. To find the centroid location, you might come over a distance, and that would be the coordinate x bar, and this would be the coordinate in the y direction, y bar. And we calculated that using a couple of integrals. The first integral we used was to say that the integral of dA would give us the total area of the shape. And then once we had that, to find the centroid location y bar, we would put that area on the bottom of the fraction. Integral of dA goes on the bottom. On the top of the fraction, we do the integral of y dA. If we wanted to find the x coordinate of the centroid, we do the same thing, but we do x dA inside of our integral on the top of the fraction and just dA on the bottom. And I want to put a little box around this thing on the top of each of these equations. This actually has a name. We don't use it very often, but this thing on the top has a name. It's called the first area moment. So this first area moment comes in to the calculation of a centroid. Well, what we're doing today, this area moment of inertia, is actually called the second area moment. And what our equation looks like is the moment of inertia about the x-axis is going to be just the integral of y squared dA. Moment of inertia about the y-axis is the integral of x squared dA. So this thing I just wrote down is called the area moment of inertia. And every once in a while, somebody might call it a second area moment because of the squared in there. Area moment of inertia is what we're going to call it, or just moment of inertia in this class. Well, you do notice a couple of really important differences between centroid equation that has an integral and the moment of inertia equation that has an integral. First of all, when we did taking an integral and dividing it by another integral, for moment of inertia, we do not divide anything. It's just one single integral and you're done. The other thing to notice, when we were finding the y coordinate of the centroid, we did the integral of y dA. So the y on the left and the y on the right match. X on the left, X on the right match when you're finding the coordinate of the centroid. When we are finding the moment of inertia about an axis, the X on the left and the y on the right do not match. And the y on the left and the x on the right do not match. And the idea here is, think of it as like the second moment, that's why we've got a squared in there, that each little bit of area causes about an axis. So if we're looking at the x-axis, and I've got a chunk of material up here, and I want to find out how big is the area moment it causes about this axis. Remember when we did moments? You're looking for a perpendicular distance when you do a moment. So even though we're summing moments about the x-axis, or we're finding the moment of inertia about the x-axis, the distance we want to use for dA is actually a y distance, which gets squared. The main mistake students make is they forget that the x and the y have to not be matching each other. They need to be different. Let's talk about the units we're going to get here. If I take an area, which is meters squared, and I multiply it by another length squared, I'm going to get units of meters to the fourth, or millimeters to the fourth, or inches to the fourth. I want to talk for just a second about conceptually what a big or a small moment of inertia means. Let's imagine I have an x-axis here, and I take a board, like a 2x12 board that you might use for a floor joist if you were building a house. And here, if I orient it this way, this is a two-dimensional picture, but the board itself actually would extend maybe many, many feet into the page. And we're looking at the end of it and standing it up vertically. I've got all these little bits of dA. Some of them are actually quite a long way away from x, and then I'm going to take that y distance and square it. So I've got areas down here close to the x-axis that basically have no distance away, but areas farther away that have big distance away. And I have areas down here below that might be a negative y. But remember, I'm going to square y. So all that matters is how far it is, and then you square that distance. So I'm going to get a value for moment of inertia if I calculate it for this rectangular area. Now, what if I orient it the other way and I lay it down flat like this? Same exact area, but do you see how what I've just done is made it so that the area is all now really close to the x-axis? So what we're going to get here is these two situations. We have the exact same area, but very different moment of inertia about the x-axis values. Again, this is a long board that goes off into the page really, really far. And you can see this if you were to take a board, like a 2x12 board, and you lay it down in this orientation, it's actually quite easy to flex and bend it. If you lay it down in this orientation, it would be really hard if you stood on it to actually see much bending. And that's why when you're doing housing construction, you stand up your floor joists like this vertically, and you don't lay them flat, because this one here on the left is much better, much higher moment of inertia about the x-axis, and it's much stiffer and much better at resisting bending. Moment of inertia is not just based on how big the area is, also based on how that area is positioned. And this is why in a lot of structural applications, you'll see I-beams a lot. It's a way to get the moment of inertia big really fast without adding a ton of weight. Add a very thin piece of material up here at the top and down here at the bottom. Now, all of that material is a long way away from the x-axis. It shoots your moment of inertia really, really high, which causes your structure to be very stiff and very strong. Let's go calculate these now for today with integrals. So here's my first example. It is a parabola on its side, and we need to calculate moment of inertia about the x-axis and moment of inertia about the y-axis. And I'm given, we're 2 meters wide and 2 meters tall. There is my equation, y squared is equal to 2x. Because we might be using horizontal or vertical strips, it might be helpful to rearrange that. So if y squared is 2x, I can write that as x equals y squared over 2, or I can write that as y is equal to the square root of 2x. So let's start with the moment of inertia about so the equation is the integral of y squared dA. Advice for you is when you're choosing whether to use a horizontal or a vertical strip, if you've already got y squareds in your equation, let's choose a dA that's going to have a dy with it. So you remember how that's going to be? It's going to be a horizontal strip. The height is dy. And I strongly recommend when you're doing these problems to actually draw your on a picture, because it helps you figure out dA. And that's the hard part of these usually is dA and then also the limits of integration. So my dA is going to be something times dy. And what that something is it's going to be the length of my strip, which is going to change as I go from the bottom to the top of my shape. And you'll notice I know that the total width is 2 meters all the way to the right edge. That is subtract off from it this little distance. This little distance right here would be the x coordinate of the curve. As we move along the curve, these points are x comma y. So you have to go over X to start your strip and then go 2 to the end. So what I'm going to put in here for my dA is 2 minus X. Right there is a spot where students make mistakes all the time. They want to just do X times dy. But if you did X times dy, you'd be doing this strip. And instead of solving for the area in here, you'd be solving for the moment of inertia of the area out here. So there's my dA. Ix is going to be the integral of y squared dA. My dA is 2 minus x dy. I don't want to have any x's mixed in there with the y's, so let's replace x with what is equal to y squared over 2. So integral of y squared times 2 minus y squared over 2 dy. And where am I integrating from? Let's figure out our limits. We're going to start at the bottom and go up to the top. So I'm integrating from y equals 0 to y equals 2 meters. At this point, I am perfectly fine for my class for you to just toss this into your calculator and let the calculator do the numerical integral for you. The 2y squared is going to become a 2y cubed over 3 when we integrate. And the y squared times the y squared, that's y to the 4th over 2. So that's going to become minus y to the 5th over 5, and we've also got a 2. So the 2 times 5 becomes a 10 in the denominator. Evaluate it from 0 to 2, and when you run that through your calculator, you should get 2.13 meters to the 4th power. And we found the moment of inertia about the x-axis. Unlike most numbers we've had in this class this semester, I am not good at telling if that is a big or small value. If I'm not even good at guesstimating if that seems reasonable. Let's find the moment of inertia about the y-axis next. Well, it's going to be the integral of x squared dA. So you remember what I said before? If you've got y squareds in here, you want a dA that has a dy. Well, since we've got an x squared in here, we want a dA that has a dx in it. So I want to switch and use a vertical strip instead of a horizontal one. So this has a width of dx. And how tall is it? Oh, it just goes from 0 up to the curve. So the height is just y. So this is a simpler dA. This dA is just going to be y dx. What if you accidentally did 2 minus y dx? Well, that'd be this little piece up here. You'd actually be finding the moment of inertia of that shape. Let's plug this in and solve it. We've got the integral of x squared y dx. Oh, I need to get rid of the y. I can't have a y mixed in there. So that's going to be integral of x squared. Remember what y is equal to? I found it already. It's the square root of 2x. So times the square root of the 2 and the x are under the square root dx. And we got to go from left to right. So starting here at x equals 0, we're going to integrate all the way over till x equals 2. So 0 to 2, pull the square root of 2 out in front, integral 0 to 2, and we'll have x to the 5 halves dx. Like I said, feel free to toss it into your calculator at this point and let the calculator do the numerical integral. Or if you want the fun practice of calculus, because you missed calculus, this is square root of 2. That becomes an x to the 7 halves divided by 7 halves. And we evaluate it from 0 to 2. Number comes out to be 4.57 meters to the 4th. So I think the only thing I could say at this point is Iy is bigger than Ix. And I think that might make a little bit of sense. Did you notice how, again, moment of inertia is a measure of how much of the material is far away. And the material that's far away from the axis gets a huge weight compared to the material that's close. So if we're looking at the x-axis, more of the material is close to the x-axis versus far. Whereas the y-axis, more of the material is far versus close. So it's the same amount of material, same area, but your Iy is going to come out a little bigger. All right, before we go on to our next example, I want to give you guys a preview of a concept we're going to use next class that is going to be super important, and it's actually kind of a tricky concept. So I want to preview it today, so when we see it next class, you're like, oh yeah, I remember seeing that before. And that is, we just found the moment of inertia about the x-axis and the y-axis. But what if I wanted the moment of inertia about a different x-axis up here, or a different y-axis over here or over here? In particular, when you're going to use this next semester for mechanics of materials, you need to find the moment of inertia about the centroidal axis. And I don't know where the centroid is. It's probably somewhere around here. So if the centroid is here and the axis is there, can you see how the distances for the material will be very different from the centroidal axis than those distances are from the x-axis? And since those distances are all squared, you're going to get a really different moment of inertia about a centroidal axis versus the x-axis on the picture. So what about the moment of inertia about a centroidal axis? Well, there is a theorem for that. It is called the parallel axis theorem. What is this parallel axis theorem? It's used when we have the moment of inertia about one axis and we want to find the moment of inertia about the centroidal axis, or the other way around. So let me give you the theorem. The theorem says that the moment of inertia about an x-axis, you could do this for the y-axis as well, it's completely analogous. Well, that's equal to the moment of inertia, we call it I bar, and then we put a little x prime on it. And the thing you have to add to it is the area of the shape times a distance in the y direction, which we're going to square. This guy is the moment of inertia about any x-axis you want. So like the x-axis we just found the moment of inertia about. This one with the bar over it, this is the moment of inertia about the centroidal x-axis, the x-axis through the centroid. A is the area of my shape, and dy is the distance between those two axes. And why is it a y distance? Because we're talking about if here's my x-axis and here's my x prime axis, there is my distance, and it's going to be measured in the y direction. Let's apply this to the example we just did. So here was our shape again. There's the x-axis, there's the y-axis, and we need to first find the centroid. Once I found the centroid, then this would be my x prime axis. And remember what we called this? The distance from the x-axis to the centroid, we called that guy y bar. That's actually going to be equal to our dy for this problem, the distance between the two axes that we're trying to find the moment of inertia of. So to do this, you'll notice I need the area. Area is the integral of dA. Hey, I already had a dA that I found before. If I'm just going to keep using dy here, going from 0 to 2, it's 2 minus y squared over 2 dy. There's our horizontal strip. That is dy, and this width here is 2 minus x, but x was y squared over 2. We have an equation for the area. We can evaluate that. That's just 2y minus y cubed over 6, evaluated from 0 to 2, comes out to be 2.67 square meters. Do you remember how big our shape was? It was 2 meters wide and 2 meters high. So if it had been a whole square, it would have been 4 meters squared. And this looks like it is, it's exactly 2/3 of 4 meters squared, because the area inside a parabola is 2/3 of this side times that side. The area outside is the 1/3. You can look that up in the tables in the back of the book if you want, or you can integrate. So we found the area. Next, I'd still need to find dy, which we decided was equal to the y coordinate of the centroid. So do you remember how we do that? I need to find y bar is going to be the integral of y dA divided by that area I just found. Well, y dA is going to be integral of y times 2 minus y squared over 2 dy from 0 to 2 divided by area when I'm done. That guy ends up being 2y squared over 2 when you integrate it, minus y to the 4th over 8. Evaluated from 0 to 2 all over the area. So number-wise, this comes out to be the top of the fraction is 2 meters cubed divided by the area, 2.67 meters squared. And we get a y coordinate of the centroid that is equal to 0.749 meters with the rounding that I did. Does that make sense? If it were a perfect square, the centroid would be 1 meter up, but because we've got some area missing at the top, the actual centroid is a little bit lower. So that passes the does it make sense test. And then we already had the moment of inertia about the x-axis. We solved that before. We had Ix is 2.13 meters to the 4th. So I think we have everything now. We have Ix, that's 2.13. We have area, that's 2.67. We have the distance in the y direction, that's y bar, 0.749. Let's plug everything in and see if we can solve. So parallel axis theorem says moment of inertia about your any old x-axis is equal to the centroidal moment of inertia plus the area times dy squared, which in this case is y bar squared. Left-hand side, I've got 2.13 meters to the 4th. On the right-hand side, I have my unknown I bar x prime. The area is 2.67 meters squared, and y bar is 0.749 meters, and you have to square that. I do see a lot of students forget to square it, but your units don't work out if you don't square it. We got meters squared here, so we got to take the meters and square it. So we'll end up with meters to the fourth. So solving, we get I bar x prime is equal to 0.637 meters to the fourth. I want to say a few things about this before we go on to our next example. It is smaller than the moment of inertia we started with, which was the 2.13. It is smaller. It should make sense looking at this equation that it will always be smaller because you got to take it, the smaller thing, and add something to it to get the moment of inertia about another axis, right? Does that kind of make sense intuitively? Your centroid is kind of right in the middle of the area, right? It's a weighted average middle kind of thing, but it's in the middle of the area, which means that all of these bits of area are closer to the centroidal axis than they are this other axis. So you're going to get bigger distances squared when you're using any other axis compared to the centroidal axis. And the farther away you get, if I did an axis all the way down here, I would have a really big moment of inertia because of how far away all these little bits of area are from that axis. So the moment of inertia is always smallest about the centroidal axis. Always. The other thing is moment of inertia is always positive. We're taking areas times distances squared. Those are all positive quantities. You can't possibly get a negative moment of inertia unless you made a mistake. I will see students sometimes get a negative when they do this process because they started with something here and then they subtracted something from it. If you do get a negative, you have made a mistake. That was a little bit of a side trip into parallel axis theorem that we are going to use again next week. Let's just go do some more basic examples to practice. So this time I have a fourth order polynomial curve and I'm trying to find the moment of inertia of that shape. So again, I'm going to use horizontal strips for one of them and vertical for the other. Shall we do Ix first? Ix is the integral of y squared dA. Since I've got y's in there, I'm going to want to use strips that have a little dy. And just like the last problem, do you see how this length is going to be 1 minus x? So my dA for this is going to be 1 minus x dy. And then I need to replace x with what it's equal to. So I need to do a little bit of math here, bring the 2 to the other side, and then take the fourth root of everything. So I get that x is equal to y over 2 all to the 1/4 power. So if I want to put that in for my dA, it's 1 minus y over 2 all to the 1/4 power dy. Ix is the integral of y squared times that dA, 1 minus y over 2 to the 1/4 power dy. And we need to go from the bottom to the top of the shape, right? We start here at the bottom and we go up to add up all those little strips. So we're integrating from 0 to 2. The y squared term is going to become a y cubed over 3. And now I need to combine y squared with y to the 1/4. So we'll do minus 1 over 2 to the 1/4 out in front. Y squared is y to the 8/4 plus 1 more is y to the 9/4. And you add 1 to that, you get y to the 13/4 divided by 13/4. Again, if you don't like doing all this integral stuff, just toss it in your calculator and let it do the numerical integral for you. And if you do, you get 0.205 meters to the fourth. Let's do Iy. It's the integral of x squared dA. And this time I want to use a vertical strip. So there's my purple vertical strip. Its width is dx. Its height is just y. And replacing that with what it's equal to, so everything's in x's, we've got 2x to the fourth dx. This is going to be an easy integral. So Iy is x squared times 2x to the fourth dx. And I need to go from the left side of the shape to the right. So I'm going from 0 to 1. And that comes out to be 2x to the 6th will become an x to the 7th divided by 7, evaluated from 0 to 1, 2/7 meters to the fourth, 0.286 meters to the fourth. I want to do one more example. This one is a little bit harder because it doesn't have numbers. Again, I'm going to use 2 different strips, a horizontal strip with a dy, and the width will be x. And then I'm also going to use a vertical strip with a dx there, and the height in this case will just be y. And for this one, I need to do just a little bit of math. I've got y as a function of x. I'd like to also get x as a function of y. And in doing that, you rearrange this and you get x is equal to b minus b over h times y. All right, so we'll do IY first this time just to mix it up. IY is the integral of x squared dA. I'm again going to use the vertical strip. So my dA is going to be y dx. I want to replace that y with h over b times b minus x. So let's plug it in. We're integrating x squared times h over b times b minus x dx. And we're going from left to right. So we'll go from 0 to b. So that first term, we'll have the h over b times b. The b's will cancel. We've got x squared h. So when I integrate that, I get x cubed h over 3. And then the other term, we got a minus sign. And what we have is an x cubed with the h over b times it. So we've got minus h over b. The x cubed becomes an x to the 4 over 4. We have to evaluate all this from 0 to b. First term is going to become b cubed h over 3 minus, and then we've got h over b times b to the 4th over 4. So this is b cubed h times 1/3 minus 1/4. If you get common denominators, that comes out to be b cubed h over 12. Okay, that is the moment of inertia about the y-axis of a triangle right here. You'll notice that the b is cubed and the h is not. If you start seeing a lot of these moments of inertia, a b and an h is the two dimensions, you're going to see we end up with a lot of one of them is cubed and the other one is not. The cubed one is always the direction that's perpendicular to your axis. Always perpendicular to your axis, because remember, we're squaring how far away things are from that axis. So the cubed one is going to be perpendicular to your axis. Now, if I were to go look up the moment of inertia of a triangle in a table, you are not going to see b cubed h over 12, because this is the moment of inertia about the y-axis, and most tables give you the moment of inertia about the centroidal axis. So why don't we practice our parallel axis theorem one more time to see what you're going to find in a table. So here's my y-axis, and I want to find the moment of inertia about my y prime axis, which is located a distance away, x bar. Let's use our equation. Parallel axis theorem says the moment of inertia about an axis, like y, is equal to the moment of inertia about the centroidal axis plus the area of the shape times the distance between those two squared, which will be x bar squared. Let's plug in what we know. On the left, we've got b cubed h over 12 for IY that we just found. Trying to solve for I bar y prime, we need to include the area of the triangle, 1/2 b times h. And then x bar, do you remember x bar for a triangle? If this side is b, the centroid is going to be 1/3 of b over. So times b over 3 squared. So my I bar y prime is going to be b cubed h over 12 minus b cubed h over 3 times 3 is 9 times 2 is 18. 1/12 minus 1/18. If you're getting common denominators, the common denominator would be 36. We'll have 336 minus 236. This comes out to be b cubed h over 36. So that is what you'll find in a table that gives moments of inertia of triangles, b cubed h over 36. Okay, last thing, let's find ix. It's the integral of y squared dA, and the dA we want to use is the blue rectangle, the horizontal one, x dy, and then we're going to replace x with what it's equal to. So we've got integral y squared x dy. So it's the integral of y squared, and x was b minus b over hy dy. And we are integrating from the bottom to the top. So we're going from 0 to h this time. We end up with y cubed b over 3 minus b over h y to the 4th over 4, evaluated from 0 to h. So we're going to end up with h cubed b over 3 minus, when you simplify it, h cubed b over 4. So the answer is h cubed b over 12. Does that look kind of familiar? We just saw a b cubed h over 12. This one is an h cubed b over 12. So we just flip the h and the b and get the exact same thing. So the reminder is, the direction that's going to be cubed is always the dimension that's perpendicular to your axis. So for finding the moment of inertia about the y-axis, it's the b that's cubed. For finding the moment of inertia about the x-axis, it's the h that gets cubed. All right, and that's how you find the moment of inertia, using integration.